Hello and welcome again to my Physical Science online video supplement series. Today's video is a lab video and we're going to do a post-quiz review for the Acceleration Lab quiz. So let's pull up the Acceleration Lab quiz. Okay, so in order to best look at this particular quiz, I'm going to pull up the entire quiz. Here is the 7 questions worth 13 points each, 91 total, and then there's one that is worth 9 points to make the whole quiz 100 points. So at this point, we should look through each of these questions and see if we can answer them based on both what's in the handout, what's in my other video walking you through how to do this lab, really both of my other videos walking you through how to do this lab, and based on what you actually might get data-wise. Therein is the key to all these lab quizzes. You have to take the data in order to actually finish them. You can't just do them based upon what the handout says you're going to do, but you can get a few of the answers off of the handout and off the other videos and so on. So let's look at this stuff. First question says, what kind of graph did you get for distance versus time? And if we actually open up this question, what we'll see is that it is in fact a multiple choice question. So you could answer that the graphs were all flat horizontal lines, they were all straight lines, they were parabolas opening up, they were parabolas opening down, they were sideways parabolas, or they were something else. So let's go back and pull up what these graphs look like. So I have right here an Excel spreadsheet, and I've put into the spreadsheet the data that I got for several trials. There's 5 trials. This is following the directions in the lab handout, which basically say that you should do multiple trials at each angle. So if we were to look at the instructions that are written here on this lab handout, basically we see that you should mark off on the ramp in even increments every 0.25 meters. There should be at least 8 marks. 10 to 12 would be better. I have therefore 12 marks on mine. And in the other video I did a sample in which I looked at a 10-degree angle. And it basically, if you look at this setup, you can see that there should be 5 different times and then an average time. And I provided to you all a spreadsheet in which you could just enter these 5 sets of times at each distance and it would calculate the average for you. So that's what that spreadsheet is that I'm looking at. So this is for 1 degree, 2 degrees, 4 degrees. And you can see the distance, you can see the times, and here is the average time. Then I created 2 other columns, one that is basically the square of the times, the other is the square of the distances. So then I have made some graphs that plot these data. The graph is basically plotting average time versus distance, and it's doing it for each of these 4 angles. So here is the average time versus distance. These are clearly not lines. If you look at this, you can see that they are curved. Of the options available, the one that most nearly matches it would be an upward opening parabola, because these are opening upward. Now, with that said, you have to do a further test to make sure that it is in fact a parabola and not, say, an exponential or a higher order polynomial, etc. I'll grant that it could hypothetically be a higher order polynomial. Theory is always underdetermined compared to data. I could make, say, a cubic function that fits through this data fairly nicely, or I could make a function that looks like y equals x to the 12 power that fits through this exactly somehow. In any case, what I've done here is I've plotted distance squared versus time, and I see that these are still curved. In fact, they are more dramatically curved. And then I plotted distance versus time squared, and I see that I now have 3 straight lines. So the implication of this is that I in fact have 3 straight lines, not for distance versus time squared. And so that implies that these right here were originally parabolas. And you can go and look at that other video that I've made discussing how to analyze parabolas in order to understand why that is. I'm not going to rehash that video right now. Okay, the second question on this quiz says, suppose you get a slope of 0.165 for the 2-degree ramp's linearized distance versus time graph. What should the units of this slope be? And then it says, note, distance is in meters and time is in seconds, so your answers should be in the SI, that is MKS, basis. And we should note again that this was a multiple choice type question. So you could pick M, that means meters, S, that means seconds. You could pick meters per second, you could pick meters per second squared, you could pick meters per second quantity squared. Notice that this and this are not the same answer. This one is the same thing as meters squared per second squared. This is just meters divided by second squared. Or the answer could be none of these options that you're given. So here is that linearized graph. Distance appears here on the y-axis, time squared appears here on the x-axis. If you want to find the slope for this graph, you pick 2 points that are on the line of best fit. So in Excel, you can actually just tell it to fit a line to the data. And if you were doing this by hand, though, you'd maybe take this graph and then try to draw a straight line that best goes through these data points. So here actually is the graph. I am not going to be able to draw a very good line because I don't have a way of setting up a ruler on here that I can follow. You should take a ruler and try to put it through these points as best you can and then draw the line going through the points. So mine's going to be a little more wiggly than yours is because I don't have the ability to do that with my setup here. But basically this could be a pretty close to good line of best fit. What you do is you pick 2 points that are on this line of best fit. So 2 places where this line goes through easily identified points, like say this point right here. And ideally you pick 2 points that are far apart. So these 2 points would work. Looking at these 2 points, this one right here, we can read off where this is and we can read off where this is, and that gives us this point. So this is in increments of 10 square seconds, and there's 1, 2, 3, 4, 5. So this is 2, 4, 6. So this is the point 6 point, let's say 0 seconds squared, comma, and then looking over here, these are also in increments 0.1, 0.2, 0.3, 0.4, 0.5. So this is 0.4 meters. Probably we don't really have the 0.0 on this particular resolution. I can actually see a better resolution on my screen than what you're going to see on the video. This point right here, in the meantime, if I were to come down here and look, it's at the 30 second squared mark, and then coming over here, this right here looks like 1.6, 1.7, 1.8. So this is 1.8, this is 30 seconds squared, comma 1.8 meters. So if I want to find the slope for the line, slope is equal to rise divided by run. So the rise in this case is the difference between the y's, the run is the difference between the x's. So delta y over delta x. So slope in this case is going to be equal to 1.8, minus 0.4, and both of those numbers are in meters. So we have meters, and we have 30 minus 6. So 30 minus 6, and both of those are in seconds squared. So for the purpose of this problem, the question was, what's the unit of slope? Well, the unit of slope would be these units right here. So unit would be meters over seconds squared. So that is what the unit of slope should be. Notice that this unit is a unit of acceleration. That matches nicely with your written directions in this lab handout. If you scroll down here, it basically says some of the graphs will not make straight lines. You can check to see if the curve is a parabola by squaring it. That's what we did in the last part of this question. Then a little while later, it says the slope of your line should be 1/2 of the ball's acceleration. That implies that the slope should have the same units as the acceleration. So your directions actually kind of had the answer to this question as well. Okay, your next question on this quiz said, suppose you get a slope of 0.168 for the 2-degree ramp's linearized distance versus time graph. What is the acceleration of the ball according to these data? Answer in proper SI units. So again, it says right here in your directions, the slope of your line should be half the ball's acceleration. So let's go ahead and write that out. Slope equals 1/2 times acceleration. Or symbolically, we would write m, because that's what you usually use for a slope, as in y equals mx plus b. So the m in that equation is the slope. So slope is 1/2 times the acceleration. So we're trying to solve for the ball's acceleration. So a, what we can do for that is we can multiply this by 2 over 1, and to do that we have to multiply this by 2 over 1, and so you get a is equal to 2 times m. So again, pulling up what the question is actually asking here, the slope is given as 0.168, and we just determined previously that that is in meters per second squared. So this is 0.168 meters per second squared for the. So at this point you have an equation that looks like this. So you may need to use your calculator. You can do it on paper with pen or in your head, or however you want, but there's no shame in pulling out your calculator if you need it. It is in fact an allowed resource for these quizzes. So plug it in, you get 0.336 meters per second squared. Okay, now as a hint on how this answer should actually be entered, think of the answer box, because you're given on the quiz a box to put something in. Think of this as saying the acceleration of the ball is, and then here's your answer box, in MKS units, which we figured out was meters per second squared. So what you put into this box to get this answer correct is 0.336. So that's what you should actually be entering here, and that's true for any question of this type. Always read back the box as if you're trying to make a complete sentence that says the whatever it is that I'm trying to find in this question is, put the number in the box, and then mentally say the units right after the number. Reason why that's important, by the way, is that sometimes it's more convenient to make marks in centimeters. So suppose we had done that. Well, our slope in this case maybe would have come out as, say, 16.8 centimeters per second squared. So it's possible that you could get some answer like this for some questions. This one, it didn't happen, but for some questions. And the question says answer in units of meters per second squared. that means that you need to convert this into meters per second squared before putting the number into the box. The reason why that happens, by the way, is that Blackboard and really any other of the convenient homework systems that I've worked with are fundamentally dumb. And they're fundamentally dumb in the sense that to make it convenient for the people writing the questions, which includes myself, the programmers of these things have set it up to where you enter exactly one number. When I enter the number, I can enter a range of acceptable numbers, but that range needs to be reasonably small if the question's answer is going to be meaningful. Small means plus or minus maybe 1 or 2%. So if you have an answer that's in the wrong units, then there's no way for Blackboard to know that you have it in those units. And so it becomes a discipline for you that you have to put it into the units that you're told to put it in. Otherwise, Blackboard's going to mark it wrong. I mention this because I consistently see in the different physical science courses that I've taught, and actually in other courses as well, that there's always a number of people who have order of magnitude problems with their answer. For example, on this problem it's not such a big deal, but on other problems I will see stuff like the answer is 33.6 meters per second squared, and that just tells me that you didn't convert your units. So having said this, let's move on to the next question. The next question is, what should be the theoretical acceleration of the ball on the ramp at 2 degree? Answer in proper MKS units. So here in the directions, the next line down in your handout for this lab says, the theoretical acceleration for an object sliding down a ramp should be 9.8 meters per second squared times sine of theta, where theta is the ramp's angle of incline. So we're dealing with a 2 degree ramp angle. So that means that the theoretical acceleration should be 9.8 meters per second squared times sine of 2 degrees. Okay, so in theory, the acceleration should be 9.8 meters per second squared times the sine of 2 degrees. Pull up our calculator, put in the sine of 2. On my calculator, I have to enter it this way. So here's the sine of 2, and now I multiply that by 9.8, and it says 0.342. So my theoretical acceleration here should be 0.342 meters per second squared. And again, if you're entering this into the box goes around this number. I'm not so sure why Blackboard has done this, but it kind of scrambled the order of the questions from how I actually entered them. This question should have immediately followed the previous one, which is what is the percent error based on the results to the previous 3 questions. Most of you got lucky in the sense that this question still occurred after these other 3. For some reason, everybody's question order was totally scrambled. I don't know why it did this. I checked on Blackboard, and it does not say scramble the order of the questions. For that matter, this right here is not where I had put this question anyway, so I'm sorry for that. Most of you got lucky though in that this came after the other questions, and so you were able to piece together exactly what it was asking for. And a few others even had it before those and still pieced together what it was asking for. I'm sorry for the confusion there. Here is how you should be answering it in any case. So it is asking for a percent error for this experiment. So sure enough, the next thing that we're told in our handout is that the percent error, which I previously labeled as PE, is the experimental value minus the theoretical value divided by the experimental value times 100%. This means that here's our experimental acceleration, here's our theoretical acceleration. So our percent error, being experiment minus theory over experiment times 100%, becomes AEX minus ATH divided by AEX times 100%. So now I plug some numbers in. 0.336 meters per second squared minus 0.342 meters per second squared divided by 0.336 meters per second squared times 100%. You should have noticed when reading this question that it states you don't need to include the percent sign or the plus or minus signs in your answer. The reason for this is that the actual way to get a percent error is that you take the absolute value of this difference, and so that means that any difference is either positive or zero, because the absolute value of any real number is itself a positive number. So this means that your percent error for this experiment, if you subtract these two from each other and then take an absolute value, becomes 0.006 meters per second squared divided by 0.336 meters per second squared, and then that's times 100%. So the units should always cancel out when doing this, because you're always trying to compare like things. So at this point, we can pull up the calculator. You have 0.006. You're going to divide it by 0.336. You get this number, and then you have to times it by 100%. And so it gets 1.785. So you could answer here that your percent error PE is equal to 1.79, for example. I usually keep only about 2 digits on a percent error. So here is what your percent error would be. You could even round it off to 2%, although I made the tolerances a little bit too strict for that, so I had to go back through and then give credit to people. Again, when you actually enter this into Blackboard, the way that you would enter it here would just be 1.8 or 1.79 or what have you. Okay, the next question is, where is the ball traveling at its fastest? So this was actually a multiple choice question, and it was meant to be a simple, easy kind of gimme question, but for some reason it proved to be more difficult for you guys than I would have thought, and I found in the past that it's been kind of difficult for people. It's multiple choice. The ball is traveling the fastest at the top of the ramp. The ball is traveling the fastest in the middle of the ramp. The ball is traveling fastest at the bottom of the ramp, or none of the above. Those are your options. So let's pull up that data again. First of all, before even pulling up the data, you should have a gut instinct for where the ball is traveling fastest. You're releasing it at the top. It starts to roll at the top. As it rolls down, it's undergoing a constant acceleration down the ramp. That means that it's picking up speed as it goes down the ramp. And the implication of that should be that the farther it travels, the faster it goes. Mathematically, we can write this in one of two ways. First, the speed is equal to the acceleration times the time. So speed is equal to acceleration times time. So it takes more time to get to the bottom than it does to get to the middle. It takes more time to get to the middle than it does to get to the top where you released it from. So that implies that the speed should be getting bigger as the ball rolls. The other way of putting this is that you may know this other equation that basically says v final squared minus v initial squared is 2 times a times d. This is the final speed, this is the initial speed. This one is 0 because you release it at the top from rest. This is basically saying that the farther it travels, this is distance traveled, the farther that the ball travels, the greater the speed should be. So it travels the greatest distance by the time it gets to the bottom of the ramp, not the middle or the top. Now let's pull up that data and have a look at it. So the other way that you can get this, if for some reason you don't have a good gut instinct as to how fast it's traveling, is go back up and look at your times. Here's for the 1 degree angle. Here's for the 2 degree angle. Here's for the 4 degree angle. And what you can do is look to see when do you have the least amount of time to get from 2 points. So basically you can do something like this. Here is the time increment that it took to get from one point to the next. And as you can see, this time increment's getting smaller. That means that the ball is getting faster. This distance increment is constant here. And I can, in fact, try this for any one of these ramps. And here it's getting smaller. And here it's getting smaller. And of these ramps, only the 4 degree ramp should pose any real difficulty in determining this, because the middle of the ramp is right here, 0.22 seconds. By the time you're at this point, these reaction times, these times in between, are kind of getting close to your reaction time, which you measured last week. Even here they kind of are, but you should at least be able to tell that in general it seems to be getting a little bit faster as it goes. And certainly for the 1 degree ramp, it's almost easy to do that. 0.4 seconds to get from 1.5 from 1.25 to 1.5, 0.3 to get from 2.75 to 2.3. If you've been doing an average, almost every one of you should have that this is faster than this. So there's 2 different ways of answering that question. And both of them are in agreement. So at this point, let's take a look at the final question of the 13 pointers, which is this question that says, rank the angles in order from angle which takes the least amount of time to reach the bottom to angle which takes the most amount of time to reach the bottom. And so, I gave you 7 different possibilities because I basically presented all the possible rankings. And it says which one takes the least amount of time to which one takes the most amount of time. So let's pull open our data once again. And depending upon your ramp size will also determine where you have to cut this off. Maybe you used only 8 data points and therefore you had a 2 meter long ramp. If that's the case, then for 1 degree angle it took you 5.7-ish seconds to get to the bottom. For a 2 degree angled ramp it took 4.05, so that's less time than this. So this one takes less time than this. If we scroll down to the 4 degree ramp, it should be 2.86 seconds. So that should take less time than this one. So the ranking, according to that, is 4, 2, 1. And let's look at the very bottom of mine, 3 meters. 7, roughly 5, roughly 3.5. So again, 4, 2, 1. So the ranking should be 4, 2, 1. 4 takes the least amount of time, 2 takes the middle amount of time, 1 takes the most amount of time. So that's what your answer should be. This one right here, you cannot, if you've been doing this experiment even close to the way that my instructions told you to do it, you cannot blame this on having bad reaction time data, because even at 2 meters for ramp length, this took an entire second and almost 3/4 of a second longer than this one is. That's way longer than your reaction time. This took an entire second and change longer than this one. That's also way longer than your reaction time. So again, that one was meant to be a gimme problem. A substantial number of people missed it anyway. The answer is 4 degrees, then 2 degrees, then 1 degree. Last but not least, we have the 9-point question. I suppose in a sense it is least because it's worth the least number of points. It says, how far apart should the marks on your ramp be in meters? So to answer that question, you can go back and look into your directions. And if you scroll up, you can look here at the example and you see that they're in 0.25 meter increments. And I basically said make the marks in your ramp in even increments every 0.25 meters. Now, you could argue that you didn't have to make it 0.25 meters. It could have been, say, 0.1 meters or what have you. But I think that it's fair enough to say that since it was asking for a numerical answer, and since I gave a numerical answer in the example and the instructions, that this is a reasonable question to ask. And so the answer is every 0.25 meters. I hope you guys realize, by the way, that it is completely fair for you to be using these instructions on your quizzes. This is one of the resources that is allowed for you to use on your lab quizzes. So you can have this open in front of you or printed off in front of you along with your calculator, along with some scratch paper, along with your data, along with whatever. You can even go and watch the YouTube video that I made walking you through this lab, although there is a timer, so it may, you may run out of time if you have to do that while taking the quiz. Okay, so at this point, I think we've answered all the questions that were on this quiz. And I hope that this was helpful for you to watch me work through all these questions. Thanks to those of you who watched these, and good luck.